Today we have a pleasure to listen the talk by Enrico Pajer from Cambridge. He will tell us about ins and outs of cosmological correlators. Okay, please, 1 hour.
Okay, thank you, Irina, and thank you, Sravan and Alexei, for the invitation to talk here. It's always a pleasure. I think I gave another talk to a similar crowd about a year ago, so it's nice to talk again about some of the updates from this program. The title of the talk is supposed to be a pun about thinking about the details of cosmological correlators and different ways that we have to think about them. So I'm going to jump into it, but as Ravan was saying, please do interrupt me during the talk. It's really going to be much more fun for everyone if you ask questions. Early on, I try to be really pedagogical and provide some motivation. So it's a great time to ask any type of conceptual questions about why are you doing this? What's the program? Where do you want to go? And later on, I'll present some recent details of a new approach that I'm pretty excited about. And part of it will be technical, but hopefully it will be clear where we are going. And so do ask questions. So I will start with a brief review of motivations for cosmology. It's just going to be one slide. I know a lot of people have heard many talks about this. And then talk about what has been so far the standard approach to make predictions for cosmology, for cosmological correlators, which is what we measure in the sky. So I'll review what we have been doing for the past 20 or 30 years, and then I'll show you that there is another way of doing it, which I will argue is simpler in certain respect and opens up the door to many new techniques that can be imported from the realm of particle physics. And I'll show you applications of this new approach. The main gist will be that instead of using the in-in formalism that famously is used for compute correlators from the early universe, I will use a different formalism that is called the in-out formalism. And at the end of the talk, I'll show you how this new formalism really connects to the idea of a scattering matrix, but instead of in Minkowski, in the Sitter space. Great. This is my usual one slide about why am I doing this, and I think why many people are interested in cosmology, and especially primordial cosmology, so the physics of the very early universe, the first fraction of a second of the Big Bang, before the hot Big Bang. And the reason why we're interested is really, for me, there's just one equation that is something spectacularly remarkable about our universe. Didn't have to be the case. You can imagine all kinds of universes that don't have this property, but ours has this property. And I think this is why people interested in high energy physics really care and should care, if they don't, about cosmology. So imagine you go out, look up in the sky, day at night, whatever you like, and measure the distribution of anything you can measure. It could be the distribution of galaxies, of photons. If you're very good, the distribution of neutrinos, even the distribution of the curvature of space-time itself. And then you make a map of this and you compute endpoint correlation function. This is what I have on the left-hand side of this equation, the expectation value of delta to some power. Delta represents any distribution. And then the promise of our standard model of cosmology is that this object is linearly proportional to the expectation value in a quantum field theory and probably in a quantum theory of gravity, or the product of some local operators that I write in red here on the right-hand side of my slide, and I call them zeta. I will say what zeta is in a second. This linear relation is only valid on large scales, but on large scales it is valid. And we know what is the linear coefficient. These functions called delta, so-called transfer functions. They depend on what you observe. If you observe photons, there is a transfer function for photons. If you observe dark matter, there is a transfer function for dark matter, and so on. But those are known within a certain cosmology. And so really cosmological observations are a probe of quantum field theory correlators on curved space-time, which is something that we haven't tested experimentally. They allow us to understand how to combine quantum field theory with general relativity, at least at the perturbative level, and perhaps to see some effects that require a treatment beyond perturbation theory. So far,
may I ask it? Excuse me. Excuse me, Enrica. May I ask some general questions? I'm confusing pure notations because in the right hand side you have
there is a typo. Yeah, sorry.
flavor PA. You
Remove the
integrate,
integral.
and
Sorry, remove
still
the
we
integral.
have envelope the same. Yes.
Remove the integral. Sorry, yeah, the integral is because I wrote it first in position space and then I went to Fourier space. Remove the integral. It's just
Okay. Now it's fine. Yes. Thank you.
in Fourier space, it's just a product. In position space, you have to do the Fourier transform of the product because it's a convolution. Yeah. Thank you. Anything else? No. Okay. So we have only seen the n equals 2 2-point function that we have measured, and we know it's primordial. That's is not a controversial statement that even if you don't believe in inflation, these objects are primordial in origin. However, we have only seen the n equals 2, but we know that for n equals 3 or higher, so for higher endpoint functions, there is a lower bound. They cannot all be 0 because gravity is a nonlinear theory. So we know that humankind will be able to measure these objects, and we will learn something about this. It's a matter of whether it happens in the next 200 years or 500 years. We don't know. But we think that this is an interesting question to study. So the aspirations is that, well, we can learn about new degrees of freedom beyond those in the standard model. We know that the statistics of this primordial perturbation cannot be generated using stuff that we have in the standard model of particle physics. We know that the scale at which inflation took place cannot be written down using scales in the standard model. We know that we need additional degrees of freedom and additional interactions. Okay, so this is a unique opportunity to probe gravity in a regime where we have never probed it, and to learn about how quantum field theory works in curved space-time. Much of what we know about quantum field theory is really intrinsically tied to Minkowski space-time, because we have developed the theory a lot for particle physics, where the curvature of space-time is not so important. And finally, it might also teach us something about quantum field theory in de Sitter space-time and whether they admit UV completions in a theory, in a consistent theory of quantum gravity. So these are some of the long-term goals. So the big picture is that we want to think about quantum field theory in de Sitter because that allows us to compute these correlators. And many different approaches to this central problem have been taken so far. In the past 4 or 5 years, a lot, or perhaps a bit more, maybe 8 by now, time goes by very quickly. Many groups worldwide have been thinking about this problem from the point of view of a wave function of the universe and its properties. And a lot of the progress that has taken place in the field of the cosmological bootstrap has had the wave function itself as the main object of investigation. This is because the wave function is somehow a simpler and more primitive object. If you know the wave function of the universe, you compute whatever you want. And because technically it's easier to compute than correlators. There is another approach, which is perhaps the oldest approach, which is don't compute the wave function, just compute the correlators. After all, those are the real observable. The wave function per se is not observable, so let's just compute the correlators. People found that the calculation of correlator is somewhat more involved for technical reasons that I will explain. Yes, and just 1 second, Deepak, and then I will come to you.
Oh, yes, there is one question.
Okay, yeah, please, Deepak.
Hi, Enrico.
Yeah, please.
Yeah, no, so when you say wave function of the universe, you mean of like the geometric and matter degrees of freedom combined, right?
Yes, yeah, there is a lot of different words being used for it. So I will try to be precise. I would use 2 kinds of words. I would use the wave function of the universe to talk about the object that includes the metric too, and that satisfies the Wheeler-DeWitt equation for canonical quantum gravity. And the other object that is somewhat related in a way that I'll discuss in a second is the field theoretic wave function. That's a field theory wave function that satisfies the Schrödinger equation and knows nothing about the Wheeler-DeWitt equation. Those are the 2 objects. Now, one, the field theory wave function is the WKB large volume limit of the wave function of the universe. So the 2 are related in this limit. Much of the recent study has been devoted to the field theoretic wave function meaning that people already take this large volume limit in which there is a large semi-classical space-time. But you're right that there is another object which has also the full quantum and non-perturbative aspects of gravity. So when I say field theoretic wave function, I mean the one that satisfies the Schrödinger equation rather than the Wheeler-DeWitt equation.
Okay, thank you.
Zravant?
Enrico, a short question. Since you're mentioning purity in crowd space-time, the profound problem of the subject is unitarity. Will you be talking in that context, or do you have some comment here about unitarity problem? Because you are mentioning S matrix as well. So, but the unitarity problem, are you solving it in some way?
Yeah, well, I could give a whole talk about unitarity, but let me just present some of the results, and unitarity will come back over and over again. We had as a group several results about unitarity at the level of the wave function, but I was not planning on discussing them today. But I have other results about unitarity that are both at the level of correlators, which I think is very useful because after all, that's what we need to compute, as well as new results at the level of a scattering matrix. So unitarity will play a big role in this talk. So we'll come back to your question several times. Okay, yes. So let's jump right into it, since there are a lot of expertise in the audience. So that the system we are thinking about is that there is a large semi-classical gravitational space-time background that is very close to the Sitter space. And in fact, for most of the talk, I will work in exactly the Sitter space, although small perturbations can be described in perturbation theory. So and then we will allow quantum perturbation on top of it. So the framework is that of a quantum field theory on core space-time. The large background is close to the Sitter, which has a conformal diagram, which is the square. And the part of the square that is relevant for cosmology is the upper triangle described here, that is charted by the Poincaré coordinates. It's called also the Poincaré patch. Coordinates are written here. They either take the standard FLRW configuration minus dt squared plus a squared dx squared, where a is an exponentially increasing scale factor e to the ht with constant h, or we can go to conformal coordinates. And at some very fundamental sense, if you knew about everything in the universe, you could define a full wave function that describes all degrees of freedom, including the metric. And if you knew where it starts at the beginning of inflation in the infinite past on this green line, and you knew the theory of the universe, you would be able to evolve it in time, and you would find the prediction on this orange horizontal line, which represent what for the Sitter is the future conformal boundary. And when in application to inflation, it represents the reheating surface where inflation transitions onto the hot Big Bang. If we are able to predict the wave function there, then we know everything about the universe, or we can directly compute correlators on that future conformal boundary. And that's what I will have in mind. For all of this talk, I will assume that the initial state was the Bunch-Davies state. I think that's by far the best motivated, and I would argue that it is the only state that satisfies two properties. One is that it is the Sitter invariant, and two, that it looks like the Minkowski vacuum on short scales. But if you have comments about modified initial state, I will be happy to discuss them too. Okay, so the wave function describes the whole system, but what we actually measure, as we said before, are correlators. When I say correlators, you can mean a variety of things. For me, mostly it will be the expectation value on the state of the universe that I denote here as omega. Supposedly it is a vector on some Hilbert space of the quantum field theory of everything, of the product of local operators that here I denote as O. Mostly I will work in Fourier space, so K is my Fourier wave number, at some time eta. Most of the time, cosmologists are interested in the equal time product. And usually that time is taken to be the asymptotic future, because we are assuming that what we observe is the end result of inflation, since none of us was there during inflation to measure an equal time correlator. So we only measure the asymptotic limit. We know how to compute this, and we have known for at least...
A very quick question. I mean, so are you going to be talking throughout in the context only of de Sitter, or are you going to consider more general cosmological backgrounds?
Mostly I have in mind the sitter, but if you have a very concrete questions about something that is not the sitter, most of what I will say will also apply to Minkowski, and depending on the result, also to any FLRW, but then I have to be specific depending on the result that I quote.
Okay, no, I'm just trying to understand how specific the results will be to more general.
Oh, yes.
Okay.
This slide is completely general for any space-time.
All right.
And we know how to compute this in perturbation theory, at least. We use what is known as the in-in formalism, in which we imagine evolving from the infinite past by turning on interactions adiabatically. So we start with the vacuum of the free theory. We turn on interaction adiabatically with an I epsilon rotation of the time integral contour, and then evolve in time until some time where we insert an operator O, and then we evolve back to generate the bra. So one time evolution generates the bra and the other generates the cat, and then we insert the operator in the middle. And we know how to do this calculation. Typically, it is done in the interaction picture, and it can be computed order by a series of Feynman diagrams. Somehow this has been the framework that started about 20 years ago from the work of first Maldacena and then Weinberg, and people have used this to make calculations in a variety of models and to study formal properties of this setup. If you want to think of it pictorially, is that you have a bra and a cat, and you have to prepare them to be in the state of the universe. You evolve them from minus infinity, where they're just a Bunch-Davies state, for some time, and then you insert the operator you want. In this sense, this is called an in-in object, because both the bra and the cat, they are prepared from the past. Okay, so the arrow represents some vector in the Hilbert space. Unitary evolution is just a rotation of this vector in this very high dimensional Hilbert space, and then you take expectation value like we do in quantum mechanics. Notice that this is very different from an amplitude. And we know how to do calculation. The details don't matter. I just want to show you what a typical calculation would require. Suppose that you have the simplest theory you can think of. It's a massless scalar. It has a phi dot cube interactions. Then just to leading order in the coupling constant of this interaction, you have to compute two diagrams. One where these perturbations interact once on the bra, and once where this perturbation interact once on the cat. Notice that the time evolution is both on the right and on the left. So there are two Hamiltonians to keep track of. One that comes from the right, minus I Hamiltonian, and one that comes from the left, plus I Hamiltonian. And because they are inside different time ordering, you see one is inside the time ordering and the other is inside an anti-time ordering, we have to keep track. So every time we want to do a calculation, even when you draw one Feynman diagram, actually it corresponds to more calculation to be done, because every vertex could come from the left or from the right. If you only have one vertex, there are two possibilities, and you have to add them up to find the right result. In fact, only when you add them up, you find the result that is real, as it's appropriate for the expectation value of a Hermitian operator. This is, for example, a typical three-point function, which is what people look for in the sky in the form of non-Gaussianities in galaxy correlations, for example.
And may I ask a question? If somebody would like to consider Euclidean version of this formalism, can you say us it is reasonable or not?
Yes, it's absolutely reasonable, and I'll show you where it sits. I will actually give an example, and I will be very close to give you a Euclidean version of it, but I will argue that there is an alternative version which is very similar, and it shares the advantages, but it has an additional advantage. So I will show you how to get the Euclidean version of this.
Okay, thank you. Thank you.
Yeah, the advantage of the Euclidean version will be that you don't have to distinguish between left and right vertices, and I will show that in a second.
Okay,
so,
thank you.
Although we know how to do this, you give me a Lagrangian, a Hamiltonian, and I just sit down and spend some time and compute. Things do get more complicated. This is the case in which we have two vertices, and now you imagine there are four possibilities. the first vertex can be left or right, and the second can be left or right. So 2 to the v possibilities if v is the number of vertices. So you can see that the number of different integrals that I have to perform for a single diagram already increases exponentially in the number of vertices because I have to keep track of these left and right vertices. And it's really essential that all of those contributions are combined together. Otherwise, the final result does not have any of the correct structures dictated by unitarity and causality. This is an example. The result of the calculation don't matter. But notice that, for example, to calculate the left diagram, where the vertices are, let's say, right, right, black, black, all of the propagators are also different. If a propagators go from a right vertex to a right vertex, then it is a GRR propagator, which is different from the GR left propagator that goes from the left to the right, because one is time ordered and the other is not. So this leads to a proliferation of different propagators with different time orderings, and then you have 2 to the v different diagrams to keep track of. So you can still do it for just a diagram with 2 vertices like this, but you can see that it gets quickly out of hand. Even though the result is... Yes, please.
What's the difference between black blob and white blob? So
black is the right and white is the left. So the blob is a vertex. It means
okay.
of the Hamiltonian. So black means it comes from this expanding this exponential to the right. So it's inside a time ordering. And white, it means that it comes from expanding this exponential. And so it means the anti-time ordering. And one and the other are not time ordered with respect to each other. In a graphical way, you can think of them as living in different branches of the in path integral, so they don't know about each other.
Is it like one is going forward in time, another one is going backward in time?
Yeah, let me show you the traditional path integral. What does it look like? It looks like this top line here. If something is white, it lives on the top path, and something is black lives on the bottom path, but they don't have a relative time ordering with respect to each other.
Okay.
So, yeah, so that's why there are different types. And this is, I mean, we know how to deal with it, but it's annoying. You just have many propagators. And the last thing is that the result is actually simpler. I mean, although it's a sum of 4 different terms that have all kind of singularities, at the end, they all cancel out each other. Each of them has an unphysical singularity that cancels out when you sum them up. And it gives you only the physical singularities, which are the partial energies of the different vertices. And some normalization factors. So it's an awkward way of doing the calculation. So this formalism actually has not at all been developed for cosmology. In fact, it was developed for completely different reasons already by Schwinger and later on by Keldysh and Feynman and Vernon to calculate out of equilibrium quantum field theory or quantum field theory for open quantum system rather than closed systems. So it is known as the Schwinger-Keldysh formalism, but it has a much wider range of applicability. What's funny about this is that the main reason in the 30s or 40s to develop this formalism was to describe open system, the classical example being Brownian motion of a particle that hits some gas around it. But in cosmology, we have only ever used it for closed system in which we claim that we are trying to describe the whole universe, all of the degrees of freedom. So we never really allow this description to actually be applied to an open system. And I think this is one of the main conceptual shortcomings of what the literature has done so far on this. And maybe I will say a few more words. In the presence of open quantum system, you have to couple the 2 branches of the path integral, and the situation is much more interesting. And you can allow for dissipations, non-unitary evolution, and so on. But I can discuss this later if people are curious.
There is a difference between the open quantum system in the standard quantum mechanical systems and then when you have gravity, you have horizons and you don't have access to any information outside the horizon. So there is a crucial difference. So I'm a bit confused how we can take the standard open quantum systems analogy with situation in gravity where we have horizons.
Oh, well, it depends really what kind of coordinates you're using. For example, in the coordinates that I'm using, the correlator that I have, they're computed on a full Cauchy hyperslice. And so I have access to all the information. The Hilbert space is the full original Hilbert space. There is no tracing over degrees of freedom being done. If you insist in working only along the word line, then you would probably be working with the static patch of the sitter, which is a smaller patch, a smaller part of the space-time that has an horizon. And if you only restrict to yourself there, then you will have to trace over the degrees of freedom that are outside. But when we work with the Poincaré patch, we have a full unitary evolution with a full Cauchy slice. You give me the initial condition, everything else is within the domain of evolution of that, the causal domain of that Cauchy slice. So I think that's not.
It doesn't matter whatever the coordinate system. The problem should be the same, no? I mean, it's just
It depends what the observable are.
Yeah.
It depends what the observable are. Yeah, of course, the coordinate system doesn't matter. But if you claim that the only thing you can observe is within the word line of a single observer, then you have that problem. However, as you know, in cosmology, we are the meta-observers of the early phase of the sitter expansion, in the sense that we are allowed to measure super Hubble correlators that if we live during inflation and if inflation went forever, we would never be able to measure. But because inflation stops and we have decelerated expansion, we are allowed to access that super horizon information that was lost to the single observer during the sitter. In that sense, I'm saying that the presence of a horizon during inflation is less, it has different type of consequences because we still measure super horizon correlations.
Okay.
Excuse me, can I say something?
Yes, please, Igor. Yeah.
Okay. You mentioned some perturbation theory for open quantum system, but you did not mention, it seems, the main result in this direction. I mean, Garini-Kazakowski-Sudarshan master equation. It started from Bogolyubov-Van Hoff results and so on. Why
Yes.
You did not mention Garini-Kazakowski-Sudarshan master equation. It is really results, not just perturbation theory.
Yes. So
this itself gives nothing. It just goes nowhere.
Yeah, so I didn't mean to give a talk on open quantum system, although I have a different talk that I can give on open quantum system, and I'm happy to come back anytime to give a whole talk about the master equation and the path integral version of this, sometimes called the Martin-Siga-Rose formulations. But I wasn't going to talk about that. I'm just saying that the same formalism is much more powerful, and we are only using it for a very restrict class of models, which is actually closed evolution, and is going to be Hamiltonian evolution rather than Liouvillean evolution. And so everything that has been done so far in cosmology is restricted to that much more constrained set of possibilities. But I think you're right, and we should do more also in cosmology. And I could talk about that, but that would be another talk.
Thanks.
So that's, thanks for pointing it out. I think it's important. I think we should keep our mind open that there is maybe a master equation to be solved. Okay, so there are many difficulties of this approach. And this has been what everyone has been doing for about 20 years to a large extent. This is the informalism compute for large classes of models. One difficulty I mentioned already is that even when you draw one diagram, it's actually 2 to the v different contributions where v is the number of vertices because each vertex can be right or left. Each contribution is in general hard to compute because it requires the calculation of nested time integrals where the integrand is the product of Hankel functions. If you're interested in fields of general masses, their mode functions are Hankel functions. So all of these propagators are actually products of Hankel functions, even at 3 level. So the calculation, even at 3 level, is very hard. This is related to the absence of time translation invariance, which makes these time integrals really actually hard to compute. And finally, even when you do a calculation for one model, you completely lose track of what were the general consequences of unitarity, locality, and causality. Of course, if you start with a unitary local and causal theory, the result will obey those properties, but you will never know what is the general relation that they need to obey in a general theory that has these fundamental principles as at its core. And so we would like to to see more general results that are not related to a single theory. And so many different progress has been made on different fronts. I will describe some recent progress that I'm excited about. And before giving you all the full details, let me give you three main messages. The first main message is the following. What I described so far, which is what has been used in the literature since the early 2000s, is this in formalism. You put these vertices, you integrate them from minus infinity to the end of time, eta equals 0, and then you sum over all possible combination of vertices being left or right, which leads to many contributions. I now claim that there is an easier way to do it, and in fact, it is much more familiar to all of us. I claim that there is another way that gives exactly the same result, in which all of the propagators are one and always the same propagator, which is the Feynman propagator, all of them, and you never have to sum over vertices coming from the left or from the right. They are all the same. And the only difference is now the integrals go from minus infinity to plus infinity. I will show that this is a sort of in-out formalism for cosmology, and it leads to a large technical simplification, and then can be used to derive new formal results that were hard to derive before. There will be a couple of technical assumptions for this equality between in and in-out formalism to be valid. One will be that there is no divergence at late time. These divergences are sometimes called infrared divergences. They arise when we push eta to 0, which is the future. So I will assume that no such divergences take place. This is the case, for example, for single field inflation, where interactions have always a sufficient number of derivatives that they become very soft in the future, and therefore they go to 0 when you push conformal time to 0, which is the future. This equality will be valid for any number of fields of any mass and spin. And I will show you that this both gives you simplification, but also gives some new conceptual way of thinking about quantum field theory in the sitter. This is the main message. There is a second way to understand this message, which is very closely related to what Irina asked before. And it is the following. So here, what I'm drawing here is the complex eta plane, where eta is conformal time. Eta goes from minus infinity to the left to 0, which is the central. And the traditional path integral that describes this theory has been performed over the yellow and green line. Those are the in contours of the path integral. Those contours prepare the two indices of the density matrix of the system, and then you can compute any correlators. Irina correctly asked, can I have a Euclidean version of this picture? And various people have discussed the Euclidean version. It corresponds to a rotation of one in contour clockwise and the other in contour counterclockwise, in such a way that this folded closed time contour becomes a straight Euclidean contours that run from minus I infinity to plus I infinity. It turns out that on that contour, this calculation can be mapped in a one-to-one fashion with very precise rules to the calculations of perturbation theory in Euclidean ADS. And a lot of the literature in recent years have been exploiting this analogy to learn something from the rich literature on ADS CFT. The new point, yeah, please, Grigoria.
So, is there any way to connect here with the gravitational path integral formalism and methods?
You mean like the non-perturbative one over full geometries?
Yeah.
Yes, the hope is that there is a connection. So far, it has been hard to really learn something about that, except for doing explicit calculations. As I said, this path integral should be thought of as the same as that path integral, where we condition on the fact that at late times there is a large de Sitter background. So in that sense, you don't allow other topologies or other islands or other wormholes to contribute. You just say it has to be de Sitter within what I'm saying. But there is definitely a connection. Within this talk, I will not discuss very much path integrals over different geometries that have different topologies. But one is a limit of the other, so they are not unrelated.
Thanks.
Thank you. So what I'm trying to propose here and what I wrote down in the previous is similar to what Irina asked about the Euclidean path integral that runs vertically, but actually I've run the whole thing horizontally. So now I propose to run the path integral from minus infinity to plus infinity. Because now the contour is straight, there is only one time ordering. Either you are to the left or to the right, and that's the time ordering. So there is only one propagator. This requires somehow a conceptual change of mind. Since the conformal time stopped at 0, and now I need to run conformal time all the way to plus infinity, I need to imagine that everything to the left is a space-time that prepares the bra of my theory, and everything to the right is a different space-time that prepares the cat. So there are two different path integrals that prepares the bra and the cat. And so I have two different de Sitter space-time that are merged together. One is an expanding de Sitter patch, which is the standard one we use. And the other is a contracting de Sitter patch where conformal time is positive instead of negative. And the scale factor goes like e to the minus ht instead of e to the plus ht. You can think of this as just being a formal mathematical identity between two calculations, but conceptually, this is the interpretation. The third way, yes, please.
Well, I just got lost physical context when you say contracting de Sitter space, but that's not the de Sitter space we have access to. Even when you have inflation, it's expanding universe. So that's a conceptual thing which I'm confused about. And another thing which you claimed in one of the slides is in the standard calculation of informalism, you have the left vertex and right vertex plus or minus, where you run the integration from minus infinity to some conformal time. Here you run the integration minus infinity to infinity, but here you have the same thing. Basically, you have the two. You have to do make the two calculations and combine them. It's the same thing in informalism and the same thing in out formalism. So I do not see clearly what is the gain, what is the simplification you're getting it. And on the top of that, confusion is related to contracting universe. What does it mean physically?
Okay, so the main gain hopefully will be clear by the end of the talk because I still haven't showed you what I do with it. But one gain is that here you have 4 terms, plus, 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 minus, 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 and minus, plus, and here you only have 1. And if you have 3 vertices, here you have 8, and here you have 1. And then
you have 1, but then you have to split the integral, right? Because the conformal time runs from either minus infinity to 0.
Yes, excellent.
Yeah.
Yes. However, we know how we have clever ways to write our propagators such that time ordering is automatically done once and for all using I epsilon prescription. As we know from Minkowski, the Feynman propagator in principle has theta function if you write it using time. But when you Fourier transform to frequency, it's just 1 over p squared plus I epsilon, and the I epsilon plays all the relevant trick of doing the theta functions if you work with time. And so instead of splitting the time integral, you can use appropriate I epsilons to find the right result in one go. So hopefully that will be clear as I show.
Okay.
And conceptually, hopefully when I do the calculation, I think mathematically there is no doubt. I'll just show you that there is an equality between two calculations. And then as for the interpretation, I think perhaps is still open. This is the first work on this. But the way I think about it is this. So we have the usual de Sitter space, which is just the lower square here, and we insert some operators, and we would like to compute their expectation value. Usually we want to prepare both the bra and the cat from the infinite past. What I'm pointing out here is that you can prepare the bra from the infinite future of another copy of the Sitter. So the bra is the blue thing, the cat is the green. As long as the bra is prepared to be the correct object, so the correct Bunch-Davies evolved, then the calculation gives exactly the same result. The advantage of preparing the bra from the future is that time runs, there is a single time ordering from minus infinity to plus infinity. And so there is a single propagator, which leads to technical simplification in the results. The conceptual simplification is that you can imagine how you could define the Sitter S matrix in which you scatter particle from this past infinity, this Big Bang line corresponding to eta equals minus infinity to plus infinity. And from that point of view, you can see that The Poincaré diagram is exactly identical to the one on Minkowski. The only
Well,
difference is, yes.
diagram is well, it looks identical, but surely 0 to infinity, one half of this diagram on the right is not the physical one, which
Well, I think it depends.
mentioned in the beginning of the talk, that you take only half of the de Sitter space and you do not have the other half. And
Well,
now you're taking into that
whether
account.
you think that the bra and the cat are two different physical quantities. In this calculation, every time we do quantum mechanics, there is a bra and a cat. And so here there are two copies of the sitter. One prepares the bra and one prepares the cat. You can say that
The
one
other
of them,
copy is not physical.
I mean, one prepares the bra, one prepares the cat. The bra is not more or less physical than the cat. They're both states in the Hilbert space. They're just prepared in a different way. So that's what I would say. But you can think of it as being a mathematical trick. If you don't like this interpretation, you can just think, this is a trick. It's completely unphysical, but if I do this integral, as Enrico tells me, to plus infinity, it will work. And I'll show you that it will.
And another question in relation to comparing with Minkowski, if I take in the de Sitter metric exponential of ht cosmological time as a coordinate runs from minus infinity to infinity, then it corresponds to conformal time running from minus infinity to 0. So this comparison, Minkowski and de Sitter, it doesn't seem to be a one-to-one correspondence, because here we are speaking about conformal time, and that is Minkowski time. So
yeah, it is not an equality. It's just an analogy. Yeah, you're right. It's an analogy. There are many different aspects of the two space-times. Very good. Okay, yes, so let's get to some details. So we talk about more concrete mathematical equations. So in incorrelators, I defined them before. Let me slightly generalize the definition of an incorrelator, in which I allow operator to be defined at different times, T1, T2, T3, and I put all those operators inside the same time ordering as the time evolution of the cat. If you take all of this time to be the same time, this is the same definition that I introduced before, which is what cosmologists compute. Otherwise, this is slightly more general. This is what I will call in correlators, and this is what everyone has computed so far. Now let me define a completely different object, which I call an in-out correlator. Now there is a single time ordering that goes from minus infinity to plus infinity, and I insert all the operators inside. And I assume that all of these operators, they are inserted at negative conformal time. So really in what we would call the standard de Sitter patch. Notice also that the I epsilon prescription here has to be opposite between the right and the left time evolution, which makes the time evolution operator formally not unitary. Although usually this can be, this is not leads to precise problems. Well, here I have different I epsilons in the infinite past and in the infinite future. See, one is negative imaginary part and the other is positive imaginary part, the two branches. And then I have to divide by this factor because I want the expectation value of the operator 1 to be 1. Here it is automatically 1 because I have u dagger and they cancel each other. While here I would have basically like an S matrix, and I know from flat space that I have to divide by the sum over all vacuum bubbles, like we do for in-out correlators in Minkowski. So these are two different objects. They have different I epsilon prescription. One has a denominator. Okay, so the claim is that these two objects actually compute the same quantity. Claim is that this B in-out that I define is the same as B in-in. You can compute them for all possible cases to all ordering perturbation theory. They will always give the same result as long as there is no divergence at eta equals 0. As long as all of these calculations are finite, so B in is a finite quantity, B in-out is a finite quantity, then those two quantities are the same. This is the claim. This claim is known in Minkowski, and people have, to some extent, perhaps used it or mentioned it in passing in various ways. Here we claim that this is also true in cosmological space-time and specifically in de Sitter. So I wanted to give you a quick argument and a few explicit checks, because now I'm worried that I will not have enough time. So let me give you a formal argument, perhaps. The formal argument is as follows. First, we notice that if we do time evolution from -infinity to +infinity of the Bunch-Davies state, the result is proportional to the Bunch-Davies state itself times a phase factor. So an infinite amount of time evolution from -infinity to +infinity does not lead you to a state excited with many particles, but it sends you back to the Bunch-Davies state. You can check explicitly this statement by projecting this on any endpoint excited state, and you will see that the projection will be 0 for physical momentum. So when we do this, then the proof is relatively simple. I'll show you in equations. You started with the in-out correlator that has just one time ordering, and then for free, you can insert this U dagger by using this expression above. Since instead of 0, I can write 0 times U up to a phase. And I have removed the phase, but it can be canceled later on. And then this U dagger cancels half of this time evolution, because one is U, one is U dagger, and the result is just the in correlator, where the first evolution is anti-time order, and the second is time order. For me, it's much easier to think of this graphically. This is the in contour. You imagine adding for free another infinitely long contour, because that acting on the vacuum is just a phase. And then these two parts of the contour cancel each other. This is what the red lines show, the cancellation. And you're left with this in-out contour, which gives the same result up to a phase. This is the formal proof that this is true, as long as all of these quantities are finite, which requires the absence of infrared divergences. Okay, the formal argument works, and it works, but how does it work in practice? There are many checks that we have performed. I'll show you one or two, just so that you can see how it works. For in, you have two terms, the right and the left. One is an integral of some Feynman propagators, the other is the integral of some Whiteman propagators. While in-out is a single calculation with all Feynman propagators. But you can cut open the integrals from -infinity to 0 and from 0 to +infinity, and you see that one term is common to both. Chandra?
Questions, please. I don't see who.
I really cannot hear much, so I don't know if it is a question or if it is maybe.
I think we can mute somebody if the speaker is not clear. They
Okay,
can write
yeah.
the question in the chat.
Sounds good. Yes, I'll continue then. And then what's beautiful about it is that the two expressions in and in out, they're not identical to each other. Actually, the difference gives you these two integrals. But you can prove by combining these integrals, the I epsilon are such that you can close the contour in the lower half complex plane, and the function you're integrating over is analytic there. And so the contour gives 0. And so the two quantities are indeed the same. This can be proven also for higher order diagrams, but I didn't report here the proof. So this is the mathematical observation. We can rewrite one calculation either in or in out, and it gives the same result. I think as a mathematical observation, it's just a true fact. Now I will show you why this is useful. So for one thing, it's useful just because you have fewer diagrams, but let me give some concrete example of how we can use it. One is this idea of pole bagging. We know that the propagators are very similar, very simple when we go to frequency space, because instead of having the two theta functions, everything goes back to an I epsilon. This is what Sravan was asking before. Do I still have to deal with the two theta function? Well, in Fourier space, you just put the correct Feynman I epsilon, and you get the time ordering right. And then this is what we do when we apply the LSZ reduction formula. So in cosmology, we can do a similar thing. Let's start in Minkowski. Suppose that I want to compute the 3-point function, and now I'm going to show you the calculation that you know. Every one of us has computed a 3-point function at some point in their life. Or if you haven't, it's a very similar calculation. I'll show you how to do it in a completely different way, which is not the in. And I argue this is somewhat at least different, and in some cases simpler. So now let me do it in Minkowski to begin with. The next slide, I will do it in the Sitter. So in Minkowski, if I work in Fourier space, this is just the product of Feynman, Feynman, Feynman. Just 3 Feynman propagators. There are 3 propagators, so this is 3 propagators. If I want to compute it at equal time, I have to do a Fourier transform in d omega 1, d omega 2, d omega 3, e to the it. So I bring from Fourier space to time. This exponent is actually 0 because by energy conservation, there is a delta function. So this is e to the I0, so I can drop the exponent. So it's just an integral in d omega of the product of Feynman propagators. The I epsilon is instructing me at which of these poles I should pick up when I compute the contour using the residue theorem. And I can just use this master equation that tells you how to pick up a pole. It's very simple, undergrad level residue theorem. And the result is exactly the one that we know and love, which is like the 3-point function 1 over total energy with the correct normalization. But it arises from a calculation in which we never really had to do basically any integral. We just collected some residues specified by the I epsilon prescription. And as you can see, I didn't have to resplit the time integral into different parts. So this is useful. This can be done for any endpoint function in Minkowski. But something similar also works in the system. For massless and conformally coupled scalars, I can write the Feynman propagator in Minkowski, in the system, the time order propagator. When I say Feynman, I mean time order, in this dispersive representation. It's just the product of the mode function divided by something that looks exactly like a Feynman propagator. And this is just equivalent. It's the same as the propagator. Once you have this expression, then the calculation works the same as in Minkowski. You take the product of some of this, and then the integral in d omega to go back to time, just pick up some residues. And indeed, you can reproduce, and in the paper we have many examples, the standard 5-point function of some conformally coupled scalar, for example. Notice again that this is just a sum over residues. We never actually perform the time integral, even though usually in the sitter you have to do all of these time integrals. They don't come for free. So here they can be traded for sum over residues. I think this is much simpler. That was the first case. Oh, there is a question. Is there a question? The result of the previous integral represents the energy. Sorry, I'm not sure. The result of this integral. So this integral has an energy, and when you do them in the sitter, is not delta functions, but it's derivatives of delta functions. So you have to keep track of that. There is no energy conservation in the sitter, but nevertheless, you can do it using the residue theorem. Let me mention the second application, which is recursion relations. These only apply in Minkowski. So maybe I will skip them. I mean, if you care about, I can show you. Maybe I'll just show the result, but I'm aware that I don't have much time, so I'll just show you the result, and then I will move on. The final result is that, again, you can, instead of computing correlators in Minkowski, you can just compute them by just multiplying and dividing. So there are some recursion relation. If you want a correlator that has an extra vertex and anything as complicated as possible in this blob, you can use that is equal to a correlator that has one fewer vertex, and you just multiply times specific factors. So like this, you can reduce an arbitrarily complicated diagram to one that has a single vertex. So this is a recursion relation to compute correlators just by algebraic means. You just multiply times these factors, and you keep track of that. You never have to do a time integral. This is a generalization, or it's very similar to some recursive relation that were developed by Erkani Hamed, Benincasa, and Postnikov for the wave function. But here we are showing that these also work for correlators. There is one third application that I wanted to discuss, which are cutting rules. We know that unitarity for amplitudes is embodied in the optical theorem, or the generalized optical theorem that says in the forward limit, the imaginary part of the amplitude is the total cross-section and therefore is positive. But for correlators, we didn't know similar arguments. And here I want to show that now that we have written correlators as an in-out, we can just copy the same derivation of Katkowski's cutting rules. And now it will apply to correlators just like it applies to amplitudes, with some small technical modification. The starting point of all of this derivation is this identity, which says that if you have the product of n operators and you divide them in two groups, and you in all possible ways, and you make the first group time order and the second anti-time order, the sum over all those things is always 0. This gives you a bunch of identities. If you insert those identities inside a correlator, then you can prove that's the sum of correlators that is 0. I'll give you just one example, which I think is particularly simple. Suppose, again, you want to compute just one interaction, and then you have n legs, or m legs on one side and n minus legs on the other, and they interact once with an arbitrary number of loops. Then we can use this identity by taking 3 different objects, or 1, or 2, or 3, and now we have to group them in all possible ways. There are only 3 ways to group them, and so we know that this quantity, if we sum them all up, it adds up to 0. Each one of these objects can be rewritten as a correlator. The first one is just the correlator we talk about. The second one is a correlator plus itself with analytical continuation of the energy. And the last one is just a different analytic continuation. So this gives us infinitely many identities. And those identities gives us new rules that correlators have to obey if the theory is unitary. Let me show just one concrete example. Suppose that your theory is unitary, then this correlator, the endpoint function with a single vertex, has to satisfy this equation. The endpoint function with a single vertex with all external energies E plus -1 to the n times the same endpoint function where all energies have been analytically continuous with a minus sign in front has to be 0. This is a necessary condition for this correlator to come from a unitary theory. This gives us a nice constraint from unitarity, which works directly at the level of observables, rather than having to start with a unitary theory. And is very useful in the philosophy of the cosmological bootstrap, which attempts to write down certain correlators just based on their general properties, rather than computing them from an explicit model. And this is the first time that we have these rules for correlators. What had been known so far in the literature was only for the wave function. And so people had to first bootstrap the wave function and then use it to compute correlators. Well, this allows you to work directly at the level of observables. We also have a nice graphical notation where this dashed line represents the energy that should be analytically continued. This works for more complicated diagrams, for example, the exchange diagram with any number of loops, or if you want, some people call this a melonic loop, because it looks like a melon. Again, there is a similar cutting rules where you cut nothing, you cut the left legs, you cut the right legs, you cut in the middle, and this sum of terms has to be 0. This gives you other relations that are necessarily satisfied for any unitary theory. There are infinite many other relations, although in the paper we were not able to give a nice compact expression for all of them. So you still have to work them out one by one. Notice that was really useful to get this relation was that we only had one propagator. All of these propagators here are just the same Feynman propagator. That what makes it so easy to derive this equation. If you instead go back to the informalism, where some are Weitmann, some are Feynman, some are anti-Feynman, it's very hard to keep track of all the contributions and write down a relation like this. So I think this is a third example of why the in-out formalism is useful. In the last -1 minute of my talk, unless there are some questions, I will talk about scattering in de Sitter, which I think is very exciting because it gives us a non-perturbative notion of unitarity in de Sitter, which I believe within the next 2 or 3 years can be used to derive finally positivity bounds for cosmology that tell us which effective field theory that we use in cosmology admit a consistent UV completion, just like we have this positivity bounds in Minkowski. I think this is a very useful result because we do have many effective field theories and we don't know if they are consistent in the ultraviolet. So because we have this picture of the in-out, we can take this in-out correlator and we can amputate the external legs. And that automatically makes us think of an object which is similar to an S matrix. More formally, let me assume that I start with a state in the infinite past eta minus infinity that has n particles. I evolve for an infinite amount of time to eta equals plus infinity, and I project onto a state with n prime particles. This is exactly what I would do in Minkowski, but with our formalism, you can also do it in de Sitter. The states are also a reducible representation of the de Sitter group rather than in the Minkowski group. So instead of being classified by mass, spin, and spin in a certain direction, now they're classified by the first Casimir, which for primary operators is related to the dilation scaling dimension. And then you can use some other quantum numbers like momentum and spin. So now you take a tensor product of those, evolve, and project. That's what an amplitude is. People have discussed about amplitudes in de Sitter for at least 20 years or more, and there are a variety of criticism to the existence of a scattering amplitude in de Sitter, but there's also been some positive construction, first by Marolf, Morrison, and Zrednicki, and more recently by Melville and Pimentel. And ours is just a third possible construction, and they're all somewhat similar. Some of the criticism is that there are IR divergences in de Sitter, and that's in general true, although here we're assuming that there aren't. Let me finish this slide, and then I'll come to you, Zravan. The second one is that particles could be unstable. That's true. However, we don't think that there is instability in the infinite past or the infinite future because we are turning off interactions. Other people are worried that particles will get blue shifted as they are evolved to eta equals minus infinity. I think this is a coordinates artifact because in the global patch, you can certainly have a particle moving through the Big Bang. And finally, there could be particle creation at eta equals 0, so there is not a good outstate, which is okay because we never use that to define our outstates. Please, Sravan.
Thanks for bringing this paper, Morris and Stednick. Actually, I was thinking about this paper all the time during the talk. So, indeed, comparing your approach to what is discussed in this paper, you also talk about the contracting branch, but maybe mathematical point of interpretation is a bit unclear here. But in their case, interpretation is very clear, as you mentioned, like, okay, there is through the Big Bang, so you have particle moving through the Big Bang, you have a contracting branch before the Big Bang and after the Big Bang, so the expanding branch. So I don't know if you can able to clarify, distinguish these two in a bit more.
Yeah, I can maybe make a drawing.
Yeah.
Maybe I'll make a drawing in the interest of time. Can you see my cursor if I move it or not?
Yeah, we can see.
Okay.
Yes, we can see. Yes.
Oh, fantastic. So what they do is the following. No, wait, how am I going to draw it? Let me draw it. Let me take the right drawing. Okay, yes. Yeah. So they start from here, like I do, eta equals minus infinity, this line. They go all the way to eta equals 0. Then they turn around, go all the way back across in the global de Sitter, all the way to the other patch, eta equals 0, but 0 plus. Then they turn around again, and they end up in the middle. So they go up, all the way down, and then halfway up. I think this is very related. So they start and end on something very similar. They start and end on this diagonal of the contracting patch and then diagonal of the expanding patch, just like I do. But they have this extra evolution from plus infinity to minus infinity in the global patch. So I think it's very close to what they define. I think it's maybe a matter of taste of how many times you like your path integral to bend. The more time folds, these folds in the path integral sometimes are called time folds. The more time folds you have, the more cumbersome it is to do the calculation because you need to triple your fields. You know how in you need to double your fields. So if you know it's pi plus or phi plus or phi minus, if you have 3 folds, you need phi 1, phi 2, phi 3, and that's okay. I think what they're doing, it probably makes a lot of sense, and I think is related to this. I just think that here there's just a single, no time folds, a single straight line from minus infinity to plus infinity, and it seems the most natural way to define in a scattering matrix. I think our in states and out states are the same as they have. It's just our time evolution straight line one, which I would argue is very simple.
Yeah. Well, and that related question in this, I kind of naively understand why your calculation works because of the symmetry of de Sitter space. If you write in conformal time, the space-time metric is symmetric under flip of the sign of eta, because it is eta square or tau square. I don't know which notation. Yeah, your conformal time. If you write the de Sitter metric for the flat FLRW coordinates, it is conformal to Minkowski with a conformal factor 1 over h square tau square. So it is symmetric under tau to minus tau. So, but you destroy this symmetry if you go to a complicated spacetime like inflation, because you depart from de Sitter symmetry and you do not have this eta to minus eta symmetry in the spacetime. So I'm wondering how this technique, how this be in equal to in out, whether it holds or not in the context of inflation. So
yeah, I think it does hold, because I don't think that eta to minus eta as a symmetry is necessary. However, I don't have written down a paper to show it because work is in progress. So I'll just have to say that we will have to wait and see. But I think it works.
Okay.
I mean, we did some preliminary calculation and it seems it works. So somehow it's not really that we are using eta to minus eta as a symmetry, but rather we are rewriting part of the integral by extending it. But you're right. I haven't proven any of that. So that's in the paper is also not proven. So it's a good point. So someone should go and critically check if it works. That's a good point. So now that we have defined an S matrix, let's just compute and see if it is interesting. And I'll show you that it has one property which I think is very interesting, which is it displays unitarity at the non-perturbative level. So let me define the simplest possible state, scalars, so we don't have to deal with spinning indices. So a state with one particle is a dagger acting on the vacuum, and we put a certain normalization in front for the relativistic normalization. Then let me define the amplitude to be the component of the S matrix where you subtract 1 and you remove the delta function. This is what we traditionally call an amplitude. Usually we remove a delta 4, a function of momentum and energy conservation in Minkowski. But in de Sitter, there is no energy conservation. So we're going to leave the delta function inside the amplitude because it's not going to be a delta function. It will be derivative of delta function. And now let's compute our first de Sitter amplitude. It's very simple. N particles, and I'm going to choose conformally coupled scalars because they have very simple mode functions. So the calculation is very simple. So if the conformally coupled fields are fields whose mass is tied to the Hubble constant, the Hubble parameter in de Sitter, which is constant by this relation, and we scatter n of them into n prime of them. And then the result of the amplitude is very simple. It's a contact amplitude, it's just this. So it's lambda, which is a coupling constant. Here I use the interaction is phi to the n plus n prime. But the result is a derivative of the delta function. So there is a delta function of energy conservation, but there are n plus n prime minus 4 derivatives thereof. Okay, so it's a different distribution. Notice that when n plus n prime is 4 exactly, this is exactly the result in Minkowski, lambda times energy conservation, which is the case because phi to the 4th is exactly a conformal interaction. So I should reproduce the Minkowski result. So this is the result. It's very simple, easy to compute. I can compute more complicated things. Let me compute an exchange diagram, 3 plus r particles in, 3 plus r particles out. Now the result is quite complicated. This is the result of the calculation. It is a sum of terms. Each one has something that looks like a Feynman propagator of the internal line, but the power changes and the numerator changes as well, and they have different powers of derivatives. So it looks a little bit like a mass. What I'm really excited about is that I claim that these amplitudes obey the standard optical theorem, the same optical theorem as amplitude in Minkowski. The optical theorem is this. The general version is this relation, A from initial to final minus A star from final to initial is equal to the sum over all possible states to go from initial to that state and from final to that state with a complex conjugate. This is the standard optical theorem. It's a consequence of unitarity. The same derivation applies here too. So we claim that this is a non-perturbative. Before you compute the amplitude, this is just a non-perturbative statement. And in fact, this is the starting point for the calculation of positivity bounds. Okay, the optical theorem is satisfied, but in a highly non-trivial way. If I compute the left-hand side of this, remember I gave you this would be just the 4-point function. It's just this quantity. It looks like a big mess. The left-hand side has two terms with two different delta function and this coefficient. The right-hand side instead was very simple. It was just a delta function with a certain number of derivatives. So how are both the same? Well, if you integrate by part these delta functions, these two rational functions magically combined, and when you take the imaginary part, they pick up the I epsilon and they give exactly what's on the right-hand side. So the optical theorem is satisfied, as it should be, but in a highly non-trivial way. And I think we will be able to use this to derive positivity bounds that are true in the sitter rather than only in the Minkowski limit. I'm aware that it's getting very late, so I will close it here. I will give you an outlook. I think this new way to compute cosmological correlator is at least useful as an alternative way of thinking of an old calculation. In some cases, it can simplify the calculation. It can give you new ideas on how to derive recursion relations, cutting rules, write down integrals using the Feynman propagator and just writing poles instead of time integrals, as well as it gives you a natural way to define the sitter scattering matrix. So I think it will be very useful in the future, and we are working on various directions related to this. So I'll stop here, and thank you very much for listening.
Okay, thank you very much for your very interesting talk. Question, please. I still not see any questions. In fact, no, I see. Grigoria, please ask your question.
So thanks for the very beautiful talk. There has been some some recent work on the sitter space and how to define algebras of observables in this kind of situations. That ordinary QFT has a von Neumann algebra of type 3. The sitter changes this algebra to type 2-1. So do you have anything to say about this? Will they have any implications in cosmology, perhaps?
Yes. So first of all, those considerations only apply to when you trace over part of a Cauchy surface of your system. If you consider the full system, a full Cauchy surface that determines all the future evolution of the system, the algebra is always type 1, the one of quantum mechanics. Issues arise only when you trace over part of the system, and if you think of being a single observer that lives in the sitter and can only measure things within its own static patch, then you want to say that you trace over outside, and that leads to the problems that, well, really, the Hilbert space wasn't a tensor product, so actually you had never been allowed to trace, and that's why formally entropies are not well defined, and the technical word is that the von Neumann algebra becomes type 3, and then you don't have states or density matrices because the trace operation does not exist. Here we are never really tracing over anything. We are assuming that we control the full system over a full Cauchy hypersurface. And so the algebra is just the standard one of quantum field theory. It's type 1, and there is no issue. I hope that there is a connection to that, but we would have to trace and perhaps see how our calculation reduce in the static patch to make a connection. So it's really, I think that the key question is, what do you think is observable? If you think is observable is only what is seen by a single observer in the sitter along a word line, then you get thrown into that discussion. Well, if you say, I'm a late universe observer and I look at meta observers that are super Hubble in the de Sitter plane, then you're thrown into this discussion. That's why there is a difference. So thanks for your question.
A follow-up, if I may, perhaps. If you want to try to describe this primordial eras through a kind of DSCFT, So perhaps you would need to have a boundary surface, or there have been progresses with a stretched horizon with the attempts to consider DS as part of ADS. And do you think that your work has any directions related to that?
Yeah, so it's very general. I think the problem is that unlike ADS CFT, there is no consensus on what we should do, or there is no single really working proposal. I think there are two classes of proposals. Some proposals, they try to put the CFT on a space-like hypersurface, like the future conformal boundary, either in the future, in the past, or both. This would be the naive thing you would do if you try to copy what you do in ADS. In ADS, it's on the time-like boundaries, and in the sitter, you have to rotate it, and it becomes in the spatial, space-like boundaries at future infinity and past infinity. What's problematic about that is that you would like not to put boundary in condition in the future and in the past, because it seems to break causality. Other people have tried to cut up the space-time by putting by hand spatial boundaries, and this is partially the proposal of Cauchy slice holography in some weak rotators. So both are good ideas, and both are being developed. I would say that so far neither of them has really shown to be the right way forward. So I think it's very interesting. Our results have very close connection to the attempt to define a CFT in this space-like hypersurface, and they tell you what are the necessary properties of that CFT. So far, even though you could call it a CFT in the sense that it's conformal invariant, we know that it does not obey any of the properties of the standard CFT, like a converging OPE expansion, for example. However, it should obey this infinite set of relations that I wrote down. For example, these cutting rules for the correlators. So it does not tell you what the CFT is, but it gives you a set of rules that it should satisfy. So I think this is the connection. So thanks for your question.
Thank you.
Okay, we still have more questions. Shravan, could you please ask your question?
Hi, Enrico. Thanks for the very nice talks. I understood a lot of things now better than it. Yeah. So, well, my question is a bit different from what I asked before. I really like these cutting rules and the way you derive them. The question is how to test them observationally. Do you have some intuition to test them? To cutting rules?
Well, as written, they are not a relation like Maldacena consistency relation, in the sense that one part of the equation is physical and the other is an unphysical kinematics, where energy is defined to be negative. So they are not testable. However, they do have consequences. So, for example, exactly these rules, if you apply them correctly, they would tell you that at tree level, you cannot have a parity odd correlators for massless scalars in the sitter. This is like a result that we derived recently. And you just apply the cutting rules, and you see that because parity odd correlators are purely imaginary rather than purely real in Fourier space, you see that they have to be zero. So the only way that they have to satisfy that relation is that they are 0 plus 0 equals 0. And so that is a phenomenological consequence. It says that if you see a parity odd galaxy trispectrum, 4-point function, it cannot arise at tree level from a massless scalar. So all of the standard construction that you would try, like the simplest one, single scalar tree level, it gives always 0. So that's an example of a phenomenological consequence. Of course, you can introduce more complicated models, break scale invariance, add spinning fields, or change the Bunch-Davis vacuum, in which these things emerge. But I think it would tell you that these observables, such as parity odd correlators, can only be associated to non-standard inflationary dynamics. So that's a way to test the consequences of unitarity. Ultimately,
but that's very indirect way. Well, and also you are speaking about specific model where you introduce parity violating terms in the Lagrangian. Am I correct?
Well, let me say it another way. It's not that in the standard model, the reason why every single quantum field theory textbook we have has a chapter on the optical theorem is not because you go to LHC and test the optical theorem. It's because you use it to compute. Because often it's easier to compute certain cross sections by using the optical theorem rather than by first computing the amplitude or not. For example, in all the cases of infrared divergences, the amplitude is actually infinite, and you believe that it resounds, and it's really through the optical theorem, through its imaginary part, that you can much easily compute the cross-section. So I think of this unitarity, we don't write them down because we think they're going to be violated, but we write them down because we think they're going to give us different ways of computing the result and or of bootstrapping the result. For example, so this is related to Grigoria's questions. Like one of the main questions of DSCFT is that what is the CFT? What property does it satisfy? If it was a CFT in ADS, we know that it would have to be a reflection positive, because that's the type of Euclidean CFT that when you Vic rotate it to Lorentzian has unitarity. However, in the sitter, we know they are not reflection positive. However, they should satisfy some other properties because of unitarity. Our relation will give you some of these properties that it needs to satisfy because of unitarity. So they're not really phenomenological predictions. They are properties that the theory satisfies. So I think they're different. They're not like Maldasena's consistency relation.
Yeah. So, well, in the analogy, you're drawing with particle physics. Well, here you're talking about correlations, right? All of them, everything you are talking about are observables. So, indeed, I mean, optical theorems in standard QFT is about understanding ghosts and also the standard formulation, but you don't test optical theorems in the LHC. That's correct. But then here in the cosmological optical theorem, you're talking about correlators. Correlators are observables. So in this sense, that's
Well,
why
but
I
not the
feel like there
analytically.
should be a way to, yeah.
Yeah, but the analytically continued one are not observable. I mean,
Yeah,
it's the same for
I see.
it's like Kramer's Kronig expression relation. All of these things that you do on the complex plane, I think they're very useful for bootstrapping amplitudes and CFT correlators, but they're not really physical kinematics. So there's the complex plane.
Right.
It's nevertheless it
So,
was the biggest discovery in physics of the 19th century.
okay. Yeah. Anyway, thanks for clarification on this. Yeah.
But you're right. It's not. It's a
Okay.
complex plane. Yeah. Luca, maybe do you have
Let's
the?
go.
Yeah. So first of all, thank you very much for your talk. It was very instructive. I have a question about one of the last slides that you showed about the optical theorem for the scattering amplitudes in the sitter. And you said that you believe that unitarity should hold at any order in perturbation theory.
But even non-perturbatively, yeah.
Right. But so at some point, if I remember correctly, you showed the largest time equation, right? In one of your slide. But at least in Minkowski, once you have the largest time equation, you can derive the cutting rules. And then from there, you can show that indeed the cutting rules are identical to what you get from the optical theorem. So you show unitarity in a way at all orders in perturbation theory, this very simple way. Can you simply do the same here in your setting, in the sitter?
In principle, yes, and I don't see why it would not work, but I cannot say that it works because I haven't done it, and it's you need to be really clever with combinatorics. These things get very messy. So I think the answer is that in principle, yes, but I haven't done it. Usually you do go the other way around. Well, it depends. The way I usually think about it is the other way around. I think optical theorem, non-perturbative, then I expand and it becomes the cutting rules. I've never done it the other way around to see how starting perturbatively you can rebuild the optical theorem. And for the wave function, I tried to do that for a few years, but I thought it was really, maybe I'm just not clever enough with combinatorics and how to write things. It's just that there are many different diagrams and you need to combine them in the right way. And it's somehow not obvious if you don't know the result to begin with. So I always try to think from optical theorem down to cutting rules rather than vice versa. But if you know the result, it's possible to go back. But if you don't, it's really hard to know which term you should combine, which you should put on the left-hand side, which one you should put on the right-hand side. For complicated diagrams, there are really many different cuts.
Because I think the original proof by Beltman, for instance, when he derived these cutting rules from the largest time equation, he somehow started from the largest time equation. Actually, in his paper, he had the smallest time equation. He started with the other way around. But he had this equation, right? And basically just showed that once you take the first term in the sum and the last term in the sum, you will have the right-hand side of your optical theorem. What remains is the left-hand side or the way around. I mean, so in
Yeah,
that
but only order by order, right? He proves it only order by order. You don't know if
at all order, at all order somehow in
yeah, but there could be some non-perturbative term that does not. It could be just non-analytic, so it doesn't expand in perturbation theory. And but we think the optical theorem is still true, even for those terms that are not perturbative.
Sure, sure.
But you're right. Veltman, in his book, actually, he does the largest rather than the smallest.
Yeah.
And without ever writing this equation, he proved this equation, the one that we are seeing now.
Yeah.
I thought it would have been nicer if he actually had written this, but
okay, so
but yeah, they should be related. Yeah, you're right that these two things
if
should.
they're not, then it means that the cutting rules that come from the largest time equation do not coincide with some, let's say, physical imaginary part that you would get from the optical theorem, right?
That's correct. Yes, I think it would be nice to convince oneself that they are related, but I think that for wave function, for correlator, I don't know. But if we talk about amplitudes, I think that what you are saying should be possible, but I have not done it. But I think it makes complete sense to me that it should work out.
Yeah, indeed. I mean, I hope it does. It would be nice to show it explicitly. Yeah. Thank you.
Okay, thanks a lot. Alexei, I'll take the last question because then I'll go out fortunately. Yes.
Okay, thank you. Thank you very much. And thanks for your talk, first of all. Look, I have a question because you repeated quite several times about positivity bounds. I'm also wondering about positivity bounds here, but you never mentioned what is your expectation if you will start deriving the positivity bounds. Do you expect them to be more restrictive than in Minkowski?
It's a very difficult question because positivity bounds are statements about effective theories. Effective theories are boxes that compute something in some regime and fail in other regime. In Minkowski, we ask these boxes, this effective theory, to compute scattering in Minkowski. In the sitter, there is also a regime in which you go sub-Hubble and you think of doing scattering and you don't even realize you are in an expanding universe. So that regime is always exists. However, the regime where we actually want to do calculation is when these perturbations are much bigger than Hubble. That's where we want to make prediction for cosmology, which is a completely different regime. So to me, it's not even obvious that the same effective field theory would describe both regimes at the same time. So I'm not sure whether there will be a one-to-one comparison, meaning an effective field theory that is valid super Hubble does not necessarily mean to exist sub-Hubble. It's a different regime because once you're super Hubble, you cannot take Hubble to zero, right? Because you take the limit of k to infinity and then you take Hubble to zero. Clearly, the limits do not commute. So
yes, sure.
So I'm not sure if it is easy to answer your question with more or less restrictive, but there could be cases in which they're incomparable because a different order of limit has been taken. K much smaller than Hubble first, and then you cannot change your mind and take Hubble to zero.
Yeah. And actually, if you allow me just some general question, because this always puzzled me on the way between cosmology which you want to test and our time, there was reheating which could change everything. How do you account this?
Yeah, so usually we invoke this adiabatic theorem or Weinberg theorem, although it had been proven by many people earlier on, that as long as the system, the theory is diff invariant, there is always one solution in which curvature perturbations are constant, no matter what the universe does during reheating. So that solution always exists. If we are in single clock inflation, where there is only one degree of freedom, then the solution of the system is zeta equals constant. So nothing can happen to zeta during reheating. If we are in
somehow we are not.
If we are in multi-field inflation, we have to wait until we land. We know that we don't see isocurvature perturbations in the universe, so eventually they have to die off. If they die off during inflation, that's great. So after inflation, nothing can happen. If this isocurvature are still active during reheating, then in principle, reheating can change the calculation, and we need to wait until this isocurvature die out before we can say that zeta is conserved. So that's correct. I would say that
because you can have immediate reheating, but it's how to say not granted, as I understand.
No, I think that the only theories of inflation that are actually predictive irrespectively of reheating are those in which this adiabatic limit, that there is only 1 degree of freedom, is reached before the end of inflation. And if
I
it
see.
is
So
before,
somehow you rely on this adiabaticity during reheating.
yes, exactly. Yes. Otherwise, you're right that you can change all kind of things. Then, yeah, you do all of this work for inflation, and then reheating changes it all. You have to start all over again.
Yeah, I see. Okay, thank you very much.
You're welcome. Thank you, Alexei.
Okay. If I see there is no more questions, so since there is no more questions, let's thanks Enrico once again. Thank you very, very much. Very instructive talk.
Thank you very much.
Thank you.
Thank you very
And
much.
before-
Thank you.
Yes, and
Yeah,
before
please send your
say
slides. I
goodbye
would be happy
for
to upload them.
everybody,
Oh, yes.
Yes,
Yes.
we make an announcement that next Friday we will have a seminar dedicated to memorial of Alexei Starobinsky. As I understand, preliminary seminar will start at 1 p.m. in European time. In the first hour, several people will tell some few words about the, I would say, cross-section with Alexei, and also his wife Lyudmila. She will also say few words. If somebody has some interesting photos, you are very welcome to show them. Then we will have a talk. Well, as I understand, the final program is not yet fixed, but approximately we can see the timetable at our site. Okay, that's all that I want to say. If somebody would like to participate in the first hour of our memorial meeting, just to say a few words or have some interesting photos, please tell us, please write to Alexei, Sravan, on Luka, or me, and just to for us to make an account how many people would like to give some small talk. Okay, thank you.
Thank you. Bye-bye.
Bye-bye.
Um,
Alexei,
Bye, everyone.
please not go out immediately. I would like to tell you something. Ричард, вы хотите, что